Right, so here we have started recording. So we're going to be looking at some more set notations. Just a few more, maybe 3 or 4, could be 2. All right, so let me get this out of the way. All right, so now we're used to the union of sets being, like if you have 2 sets being you find a union of them, a union. So you have 2 sets there having a union for the 2 sets. But sometimes you're having a union for, this could have been 3 sets, 4 sets, 5 sets, whatever. Put that. Maybe say 10 sets in all. We'll go to 10. But there are times when you have to unite an infinite number of sets in real analysis. So to denote that now, it is written like this. Let's say we have a collection of sets from A1, A2, A3, right up to whatever. So it's an infinite collection. You can't number them. And you want to have the union. It can be written like this. So it's the union. Let's see, an infinite union starting from n equal 1 up to n equal, well, it doesn't have a number. So that union is the set containing x such that x is in the set A. So that is for some n in the natural numbers. All right. So if you want to unite all the sets from A equal 1, from A1, A2, A3 right up to infinity, it's written like this. Watch that second part, very important. So it's x, the x is such that x is a part of the set A1, A2, A3 right up to infinity for some n. That some n part is going to be important.
Sir, morning.
Morning.
Sir, how you start without me? And then you know, say, Managa can catch up.
We said to start 5 minutes after. I started 4 minutes after, but
Exactly. You know, for me, I try to get in.
but I did start immediately. We just prayed and then we started. Because I came in, I think, 2 minutes late. Either 1 or 2. I would have started a minute ago or 2 minutes ago.
And now I can't even find my books.
So this is for the union of an infinite number of sets from A1, A2, A3 right up to, as you can see, the n goes from 1 to infinity.
Which course is we're doing? Which course is this?
Analysis. All right. So now if you have an intersection of an infinite number of sets, just like this one a while ago, you're intersecting. So let's make clear this sets I'm talking about. We're talking about A1, A2, A3, right up to wherever. So it's an infinite collection of sets. Now, if you want to unite all those sets, it's written like the way we had it above. The union from 1 up to infinity of an. And of course, the definition is in the bracket. It will create the set where x is from it's all the elements in the sets put together. That's what that notation in the second bracket means, for some n in n. Let me show you why that is important to understand. Look at this one now. So the English again might trick some people. So look at this. The intersection of all the sets. What's his name again? Jermaine, turn off your mic. Thank you. So an intersection of all the sets now would be like this. Oh geez, I wrote the same thing again. That's supposed to be an N, not a U. Get that quickly. Sorry about that. I didn't want to clear it, But anyway, I wanted to compare them, but I can't clear the board unless I clear everything. Something with the system. I don't like what that infinity, n equal 1 from all the ends. So now this is the set of elements x such that x is in the set A. However, this is for all n in natural numbers. So why is this one for all n? The one before was for some n. That's what I want to get to. All right, let me write it down below. The union means it's union from n to infinity, where x is in A. I forgot a little bit epsilon. X is in an for some n in n. So why is it for the intersection? It is in all, but then for the union it is in some, or for some n in m. Remember the natural numbers will be 1, 2, 3, 4, right up to infinity. But for the union it says for some, but for the intersection it says for all n. What do you think the difference is right there? Why is it that one is some and one is all? And the all is for all. So the all is for intersection where the sum is for the union. What do you think is happening there? Anybody understand? What the English behind that?
Sir, is it because a set may contain numbers outside of natural numbers? If it's an intersection, that means that everything is common, but if it's a union, then a set may contain numbers that are not natural. So it's not all of them are natural numbers.
You're saying the right thing, but the mistake you're making is the natural part, outside of the natural.
Oh, so it's just that not all the numbers are common in the union.
That's right. See, you're correct. You get it now. That's the part I wanted to get to. For the intersection, it says the x must be in each of those. I'm writing down here. It must be in A1, it must be in A2, it must be in A3, it must be in A4, and so on. That's why it says the X. Look at the top one that I wrote last. Well, I wrote the union before, but I wrote it again. But at the top we have, let me read it for you now. It's saying the intersection of this all the sets from 1 to infinity, the ones that I wrote down here at the bottom, from 1 up to, of course, you know, we don't have infinity, but let me just write it still. Up to the last possible set that we can have. There are infinite number of them. There's no set that I can call A infinity because there's no, it doesn't end. But I'm just saying, you know, it goes right up to infinity. Now, if you intersect all these sets that I'm circling down here, if you intersect all of them, the top thing is saying X is an element. So the set, it contains a set of elements X such that X is in all those sets. You see the part where it says for all and in natural numbers, that's what it means. Simply put, X is in all of those sets. So the only way you can have an intersection of all the sets and get a result is if that result is found in all the sets. That's what the top part is saying there. Now the bottom part where they use the word sum is that you're going to unite the set, unite all the sets, unite all the sets there from 1, A to A3 right up to infinity. And the result is the set of elements X such that X is found in some of them. Now, I said, but sir, the sum that don't mean that it makes no sense. What? So it don't use all of them? Yes, it uses all of them. But the reason why they say some rather than all is because for the X to be in the union, it doesn't have to be found in all the sets. Just found in some of the sets. Like some of the sets might have 1, 2, 3, next one have 1, 2, 3, 4. So even though the 4 is a part of the answer, it was not found in all the sets, it was just found in some of them. That's what they're saying right there. So let me repeat that to make sure you understand. When they say the X is equal to the union is equal to all the x such that the x is found in some of the sets. It's not saying that we don't use all the sets. It's saying that if you have, for example, again, one set with ABC and next set with ABCDE, even though the D and the E is in the result, it was only found in some of the sets. It was not found in all the sets. It was only found in some. So the result will have A, B, C, D, and E, but the D and E was only found in some. It was not found in all. Whereas for the intersection, the results that you get must be found in all the sets. Do we understand that? Any questions about that? I'll just make you understand how the wording is, why they use some instead of all.
Sir,
Sorry, but I understand. Good. Go ahead.
Sir, I understand why they use some and all, but I don't understand the
notation.
is it a case, is the natural part, sir, is it a case where you can have a set that has natural numbers and probably irrational numbers, and is it a case where that can happen, and if
Yeah,
so,
man. Yeah,
then
man.
so sir,
Hold on.
then
You see, the natural number part is not specifying the type of x, you know. The natural number is just this part right here. I'm going to put it in red or circle it in red. The natural numbers part just talks about this, that number right here.
oh, okay, so,
It does say that n must be a natural number. See, we don't
okay,
have A1, A2, A3, A4. It's just talking about those.
okay, sir.
Right. Any other questions or concerns? Right. So hopefully you guys have written that. So we're going to come later to, we're going to be using these later, but I'm just getting them out of the way from now. Now you can also have sets that are indexed with two integers. Let me show what I mean. You can have sets like this, where you have A1, 1. I don't like what that looking right again. A1, comma, 1. You can have A1, 2, 1, A1, 3, and so forth. A2, 1, A3, 1, A2, 2. Right. So when you have sets indexed like that now, to write the union for that, you have to write like this. Let's say there are infinite number of them again. So it contains all the possible numbers there. A1, 1, A1, 2, A1, 3, A1, 4, A1, 5, A2, 2, A2, 1, whatever. All of them. If you want to unite all of those now, it's written like this. It is the union from n equal 1 and the union from m equal 1 of the indexed sets n and m. So of course n and m are once again natural numbers, and that would result in this. It's the union. This is an expected story. The union from n equal 1 of all unions. That's a union up there. I mean infinity at the top. M equal 1 of a and m. So that's, you can write it the first way or the second way. Both of them mean the same thing. So don't be confused by this. I mean, when you start seeing it, it'll make more sense. Because we're going to start off with finite numbers first, so you get an idea of what is happening. But when you just, this is just the infinite notation for union and intersection. I'm not sure what part you want me to repeat, Lafern. I said a whole heap of things.
Sir, repeat the union, just repeat the union, what that means, the wording.
Oh, so this is the union of indexed sets. So if you have sets A11, A12, A13, A31, and you want to have an infinite union of them because there are infinite number of sets, it is the first part is saying it's a union from n equal 1 to infinity of the union from m equal 1 to infinity of the indexed sets. So it means you're uniting all of those sets from 1 to infinity for n. So the first part here, let's say using the first set, it would be A11. And then when you keep increasing the m, it'll be A12, A13. So you're just uniting all of those sets. That's what that thing is saying. The one on the right is saying the same thing, but what you could do first is if you look at the bracket over here, look at the bracket on the right. We're just keeping the n as n, and you're going to be, so you're going to have from the, on the part in the bracket alone. Let me show you what it will look like. It will look like this: a n1, a n2. Of course, there's a comma between, but I come right to the comma. A n3. You'll be uniting all of those, and then you put in the ones after that now. So to the left side, when you finish putting all of those from the brackets there, you're going to now put in numbers 1 up to infinity for the n. So you're going to have a11, a12, a13. Finish with the ones. Then you go to 2, a21, a22, a23. The two results are the same, just that there are different ways of writing them. On the left side, you can jumble the numbers as much as you want, but on the right side, it's just more uniformed. But it's the same end result, uniting all of them from a11 up to a infinity. It's just a fancy way of writing it. So don't be confused about what is happening. It's a fancy way of writing. All right.
Sir, and as you go along in the course, you will do working with this so that we can get a better understanding of it.
Yeah, man. Yeah, man. We just put it one time. I don't see it again. I'm just introducing it to it now, so that when we're using it, you know what we're doing.
Okay,
no
sir.
worries. The first time you see these things is going to be confusing because
And
you
it
cannot use the
definitely,
symbol.
it definitely is.
All right. So let me not do any more of these until we get to the topic that involves it. So let me go to the topic that we need to get to now. What time is it? 10, 11, 20, 1 hour left. All right, induction. I don't think anybody's writing. All right, so induction is our topic now. So some of you would have seen this in, I think it's advanced, maybe. And then we did it again in topics in math. Or was it modern algebra? I think it's modern algebra. You're going to see it again now. A little differently though. The first part is the same. So let's see if you remember. All right. The first thing you need to know for induction before we even get into it, because remember we're using natural numbers mostly. But that's not all we're going to be using. We're going to use real numbers as well. But we're going to have the concept. Induction generally works, or shouldn't I say generally works. Most induction questions include natural numbers. But of course, it can include real numbers as well, as you will see soon. The first thing you need to know about natural numbers is this. Write this down. This is our rule for natural numbers. Every non-empty subset, so the set has something in there, it's not empty. Every non-empty subset of n as in natural numbers, has a least element. Every non-empty subset of n has a least element. You can put in brackets smallest element. Every one of them. Because you know natural numbers start from 1. So you know if you're going to take a subset from it, it must start from somewhere. It has a least element. You can't find the smallest number in the set. All right, so that's one rule for natural numbers. The reason that is important to know is because if it is a real number subset, if it's a real number set, it doesn't have to necessarily have a smallest element. Let me show you what I mean. Look at this. Suppose you're just looking at negative numbers from real numbers. As a matter of fact, those negative numbers in general, it doesn't have to be real. Can you find a least element from the negative numbers?
No, sir.
No, it doesn't have any smallest element. Even if you have a set like this. So modern algebra students have seen it yesterday. You have a set like this. 0, say 10. It has a largest element. The largest element in that set is 10. What is the smallest element in here?
We don't know.
Don't know. Because if you use a 0.1, I'll say 0.01. It does divide it by 10 each time. You cannot find the smallest number in that set. You can find the largest one, which is 10, because it's closed at 10, but it's open at 0. So you can't find the smallest element in that set. But if you were the natural number subset now, you could say the smallest element in that set is 1. Not 0, no. 0 is not included in the set if you're using natural numbers. But if it's real numbers, you won't be able to find the smallest number in that set. So that's why that thing about natural numbers having a least element is important. All right, so write these principles of induction now. There are 2 ways induction can be done.
So it's just one rule?
Well, I have to establish that rule first before we can start using induction for the other stuff.
Okay.
There are many rules for it, but that's the one property that's important right now. Or I shouldn't say many rules, many properties. That was one property. I shouldn't have called it a rule. One property. All right. So you soon see why we use that property for this. So write this principle of induction. There are 2 of them. Call it principle number 1. Then I'll read principle number 2 as well. So principle number 1 says, let P of n, right on the board, P of n, like you have f of x, let P of n be a statement depending, let P of n be a statement depending on a natural number n. So it could have been P of 2, P of 3, P of 4. It's a natural number. So let P of n be a statement depending on a natural number n. Full stop. So here's how the induction works now. This is principle number 1, you know. Part 1. First thing we have to show is that P of 1 is true. That's what they call a basis statement. Show that P of 1 is true. Put in brackets or P of the least element. Sure. This thing looks so small on the board. So first step, show that P of 1 is true or P of the least element, because the least element doesn't have to be 1. But generally it is 1, but it doesn't have to be. So the first step is to show that the P of the first element, sorry, the least element is true. Step 2, assume P of n is true. Assume P of n is true. Then show P of n plus 1 is true as well. Assume P of n is true, then show P of n plus 1 is true. All right. So for those of you that did modern algebra, you understand why this works already. But if you haven't, the logic behind it is this. If you show that the first element is true, right? And then you assume that, okay, for any n, it is true as well. And you can show that if after that, for any n it is true, then for the next n, it will also be true. The next n is n plus 1. So what you're doing is this. Let's say we have 1, 2, 3, 4, 5, 6. Let's say it's 10 elements in there. Instead of showing that it is true for all the 10 elements, it could be 100, matter of fact, let's say it's 100 elements. Instead of showing that it is true for all 100 elements, which would take a lot of time, you prove that it is true for the first one. Then you say, okay, assume that it is true for any n from 1 to 100. Assume it is true for any n from 1 to 100. So you assume that, if you can show that if it is true, if the assumption that it is true for any n shows that it will be true for any n that comes after that, then you have proven everything. Because watch this. You see, if you have shown that the first one is true, the first element 1 is true, and you assume that it is true for any n after that, and you can then show that once it is true for any n, it is true for any n plus 1, that would mean this. Let's say the first n was 1 then. You have shown already that if one n is true, then it will be true for any one after that. Then if it's true for 1, then it will be true for 2. If it's true for 2, then it's true for 3. If it's true for 3, then it's true for 4, right up to 100. So that's why all you have to do is prove that the first one is true, and then if it is true for any n, it will be true for the next n. Once you have done that, then it will just flow right on to the end. As long as you have shown that it's true for the first one. If you had started with the 3, and then you prove that it's true for anyone after that, then it will be true for 3, 4, 5, 6, 7, right up to 100. But you would not have dealt with the 1 and the 2. So that's why the first step is show that it is true for the first one, and then show that it is true for anyone that follows after that. And then it will be true for all of them. So that's the basis of this induction method. All right. Principle number 2. Principle number 2. So here's what it says. Same thing as the first part. Let P of n be a statement depending on a natural number n. So this is principle number 2. That was the first principle of induction. This is the second principle. Let P of n be a statement depending on a natural number n. Oops. All right. So step number 2, having done that, having set the P of n, same was statement number 2. Step number 1, same thing as before. Show that P of 1 is true. Sorry. Show that P of...
Before you go to step number 1, you said let P of n be a statement depending on the natural.
On a natural number n.
Depending on a natural number n.
Right. The same you had written before, you had written that same thing for principle number 1. If you look back, you'll see.
Okay. Oh, yes, sir.
Yeah.
Okay. All right, continue.
All right, so step number 1, show that P of 1 is true. Same thing as step number 1 again. Same thing as principle number 1. So the first 2 steps are the same. Our first 2 things are the same. So show that P of 1 is true. Step number 2 is a little different now. Assume P of k is true. Assume P of k is true for all k equal 1, 2, 3, right up to n. So assume P of k is true for all k equal 1, 2, 3, 4, 5, right up to n. All right. Having done that, now then show P of k, sorry, then show P of n plus 1 is true.
Sir, could you repeat it again, the second one, please?
All right. So step number 2, show that if P of k, sorry, assume P of k is true for all k equal 1, 2, right up to n. Assume P of k is true. P of k is true for all k equal 1, 2, 3, 4, right up to n. Then prove P of n plus 1 is true. So I'm going to show you two examples for these two, so you see how each of them are different. For the first one, you're just looking at specific ends, but for the second one, it kind of, you have to use the 1, the 2, the 3 right up to the n. So if your n is 4, it will involve 1, 2, 3, and 4. Whereas if, well, you will see what I mean. So let me show you an example of the first one. Oh, by the way, so once you have shown these things for, once you have proven these, it means that P of n is true for all n. I should have mentioned that, Once you have shown that step 1 and 2 is fulfilled, it means that P of n is true for all n. P of n is true for all n in n, unless there are some restrictions. Sometimes they don't use all the n's, but that's what it means. P of n is true for all n in n. Once you have shown that everything is true before, that 1 and 2 is fulfilled. All right, so let me bring some sense to the definitions, because these things are better understood with examples. So first example I'm going to give you, let me find a nice one. All right, let's do this one then. All right. Here's the question that we're going to look at first. We're going to do some induction now. Prove that for all n in n, so prove that for all n in the natural numbers. So prove that for all the thing on the board, for all n in n, 2 to the n minus 1, so the n minus 1 is in the exponent. Prove that for all n in n, 2 to the n minus 1 is less than or equal to n factorial. So you guys remember what n factorial is? Well, I know Lafern and Anthony should remember, but I'm not
Yes, sir.
sure. You remember? Okay. Once you remember, that's good. Because the rest of them would see it a lot. Michaela, Lafern, and Anthony. All right. So we know n factorial is 1 times 2 right up to whatever. No. So the first step is to do what? Based on the steps I gave you a while ago, what's the first thing we need to do? What's step number 1? Hello? Oh, all right.
Yes, let's show that the Pn is true.
That's the first step. Remember, first step starts at 1, We already have the statement. Our P of n is what I just wrote a while ago. P of n, the statement that we have is 2 to the n minus 1 is less than or equal to n factorial. That is our statement that we need to use. So what's the first thing we do after this? We show that this is true for what? I'm sorry, go ahead, friend.
Show that P of 1 is true.
Good. We just make sure the statement is true for P of 1. So we just put it in there now. So P of 1 would be 2 to the 1 minus 1. And we're checking, we're not sure yet, if it is less than n factorial. Lord of mercy, 1 factorial. I don't like marking up the board, 1 factorial. So 2 to the 0, we know is less than or equal to 1, because 1 is less than or equal to 1. So it is true for n equal 1. It is a true statement when n is 1. Okay, I might have to start using the whiteboard. Oh, it's working out all right. All right, so far we have shown that it is true for n equal 1. Oh, by the way, this is using the first principle I showed you a while ago. We're just using specific numbers, using n equal 1, n equal 2, n equal 3, right, and so forth. I'm going to show you the second step, second principle after this. So far, it is true for n equal 1. Is anyone writing this?
I'm through, sir. I can continue if the others are through.
All right. I would say something, so let me just erase that now. So we're going to check it for n equal. We're going to assume that p of n is true. Some textbooks and some other people use k, so that is the difference, that you're not assuming the whole statement is true already. But it doesn't matter what letter you use. The same, you have to do the same thing. Show that p of n plus 1 is true. So we're assuming p of n is true. I should write the word assume at the front. Assume. So what that means is we're assuming that 2 to the n minus 1 is less than or equal to n factorial. If that is the case, we need to check if it is true for n plus 1. All right. So here's what we can do. To make this work, remember, you know, oh, by the way, for this to be true, let me show you what is going to happen. Because you see, when you're doing these, you need to know what you're heading towards. We need to show that 2 to the n plus 1 minus 1 is less than or equal to, oh boy, maybe I can make it squeezing, n plus 1 factorial. I can't even see the factorial. Yeah, see there. That's what we want to show. We want to get to this stage. So in essence, 2 to the n is less than or equal to n plus 1 factorial, right above. We want to show this. 2 to the n is less than or equal to. That is our goal. If we have shown this, then we have proved that p of n plus 1 is true. Now, here is what is important. You see, for you to use these induction steps, you have to use what you have assumed to prove what you want to get to. All right? You have to use what you have assumed to prove what you want to get to. So let us see how we use that this assumption right here, the one underlined in blue, or underlined with the blue line. We need to show how that, we need to use that to get to what we want to get over there. So here is what we can do. We can multiply both sides by 2. So I'm going to do it slowly. I'm going to multiply both sides by 2. So 2 times the left side. So we know that when you're using equations or inequalities, as long as you do the same thing to both sides, everything is fine. So I've multiplied both sides by 2. And right away we get the left side. We get the 2 to the n. Because, you know, this is 2 to the 1 times 2 to the n minus 1. So you add the powers, which gives you 2 to the n. Now, so this is what we have so far. 2 to the n is less than or equal to 2 times n factorial. It's not 2n factorial, you know. It's 2 times n factorial. I don't put it in brackets here. Remove confusion. All right. Now, follow me carefully now. The n's that we can use right here. What are the possible n's that we can have? Start from the smallest one and go to the highest. Well, let's keep counting up. What is the smallest n that we can have?
Sir, 1 because it's natural numbers.
Correct, because n is a natural number. The smallest n we can have is 1. And it will go up to 1, 2, 3, 4, whatever. So what that means, you know, if the smallest n that we can have is 1, it means, let me write this using a different color. It means that 2 is less than or equal to n plus 1 all the time. 2 is always less than or equal to n plus 1 because n is 1. Sorry, the smallest n you can have is 1. N could be 10, 12, 100, but the smallest one you can have is 1. So because of that, 2 is always less than or equal to n plus 1. All right? Which means that 2 times n factorial must always be less than or equal to n plus 1 times n factorial. Do we agree with that? Since 2 is less than or equal to n plus 1, it means that 2 times n, let me bracket it so what we're comparing. These are the two things we're comparing. So the 2 and in the bracket over there we have n plus 1. We have shown, or we have agreed that since the smallest n that we can have is 1, then 2 must be less than or equal to n plus 1. Because n could be 1, that's 2, n could be 2, that's 3, n could be 4, that's 5. No matter what, 2 is always going to be smaller than or equal to that. Good. So since 2 is always less than or equal to that, it means that when you multiply n factorial by 2, it must always be less than or equal to n factorial multiplied by n plus 1. Let me know if you understand what I'm saying so far. You following that? All right, that means yes. Good. So having established that now, follow me closely now. Look at that thing over there. What is n plus 1 times n factorial equal to? What's a simple way of writing that? N plus 1 times n factorial is the same as what? Nobody knows? All right, use a different color up here. Watch this little box up here. I'm going to write something in the box, and you'll tell me if you figure it out. What is 5 times 4 factorial equal to? Write it as 1 factorial. What number can we write there? 5 times 4 factorial is the same as what factorial? Anybody?
5 factorial.
5 factorial. Exactly. If you multiply the last number by the next number, you just get the next factorial. So 6 times 5 factorial is a 6 factorial. 7 times 6 factorial is 7 factorial. 100 times 99 factorial is 100 factorial. Okay, let's multiply up to the next n. Remember that n factorial means 1 times 2 times 3 times 4 right up to n. So if you multiply the next number by the previous factorial, you're getting, I don't like what's that. If you multiply 9 by 8 factorial, you're getting 9 factorial. So back to what I just asked you. If you multiply n plus 1 times n factorial, what are you going to get?
N plus 1 factorial.
Lafern, if you come in my class, you look a sleepy voice, you see. Sure. Yes, n plus 1 factorial. Oh, sorry, that's not less than, it's equal to it. This is equal to n plus 1 factorial. So we have shown that 2 times n factorial is less than or equal to n plus 1 factorial. So if you use that information, this bit of information right here, and go back to this next step now, follow me carefully. On the left, you see we have 2 times n factorial. That's what we have, So watch me now, I'm going to write everything in one line. That means that 2 to the n is less than or equal to, I was writing the same thing a while ago, 2 times n factorial, which is less than or equal to n plus 1 factorial. We'll just show that a while ago on the right side. So if the left side is smaller than the middle, and the middle is smaller than or equal to the right, it means that the left side, 2 to the n, must be less than or equal to n plus 1 factorial, which is what we wanted to show. Therefore, the original statement we had, the one I underlined with the blue lines, is true for all n. Therefore, P of n, therefore, P of n is true. What am I writing? It's bad. True for all n in n. True for all, blah, 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 for all n in n. All right, so let me go from the top quickly. Make sure you understand everything I just did a while ago. I know there's a lot of stuff. I wish I had my classroom right now. So from the top, we showed that the statement that I underlined right there, we showed that when n is 1, that is true. We just put 1 in both sides, and we got 2 to the 0 is less than or equal to 1 factorial, which is true. 2 to the 0 is 1, and 1 is less than or equal to 1. So it was true for n equal 1. To go to the second step now, we assume that the statement is true for all n. and we use it to show that we show that the statement P of n is true. Not for all n, beg pardon. We assume that the statement P of n is true. And having done that, we now need to use that statement to show that P of n plus 1 is true. So we went about it by doing this. We multiplied both sides by 2, which brought us to the line right here, in the first blue line, that 2 times 2 to the n minus 1 is 2 to the n. And 2 times n factorial is just 2 times n factorial. We then went on to show now that 2 times n factorial must be less than n plus 1 factorial. We did that by first showing that 2 is less than or equal to n plus 1, because n must be 1 or more. So since n is 1 or more, then 2 must be less than or equal to that 1 or more plus 1. So having shown that, we then went on to the next line to show that n plus 1 times n factorial is always bigger than or equal to 2 times n factorial. In other words, 2 times n factorial is less than or equal to n plus 1 factorial, which brought us to the final part on the left side there at the bottom. That 2 to the n must be less than or equal to n plus 1 factorial. All right. So this is one of the tough ones, but tough because you have to figure out that you must multiply both sides by 2. But I suppose after you get used to them, you will know what to do.
Take a deep breath. All right, so where we have the 2 over bracket 2n minus 1 is less than or equal to 2 over bracket n factorial close bracket. How did you end up with 2n less than or equal to 2n over bracket close bracket n factorial? The second right there.
Oh, you're talking the 2 blue lines there, the 2 blue writings?
Yeah, so I move from the top to the bottom.
All right. What is 2 to the 3 times 2 to the 4?
2 times 3?
No. 2 to the 3rd power times 2 to the 4th power is equal to 2 to the what?
2 to the 3rd, let me write that down. 2 to the 3rd power is equal to 2 to the...
No. 2 to the 3rd times 2 to the 4 is equal to what? 2 to the what?
This is indices. This will be 2 to the 7.
All right. So how did you get the 7?
By adding both powers.
You add the 3 and the 4. Right? All right, so go
Yes.
back to what you're asking me now. You asked me, how is it that 2 times 2 to the 2n minus 1 is equal to 2 to the n?
Okay, so you had both, because 2 to the 1 times that, so that equal to, at both powers, end up with
2 to the n.
Oh,
1 plus n
and then 1
minus 1
minus 1. Oh,
right.
let me write that.
Any other question?
Hold on, sir.
Yeah, more. Oh.
Okay, all right, so then from there, what's the step from there, sir? What you did from there, sir? With the 2 to the n less than or equal to 2 to the n factorial.
All right, so from that we went across to here. So next I showed you that 2 is always less than or equal to n plus 1. The number 2 must be less than or equal to n plus 1 because n has to be 1 or more. So that means that 2 will be less than 1 plus 1. Sorry, less than or equal to 1 plus 1. It's less than or equal to 2 plus 1. It's less than or equal to 3 plus 1, and so forth. Right. So because 2 is always less than or equal to n plus 1, if you multiply both sides of that by n factorial, it will still be true. So what I did was multiply the 2 by n factorial, multiply the n plus 1 by n factorial. That's what I did for the next line. Is that?
Yes, sir.
Let's multiply both of those by n factorial. And then n plus 1 factorial, sorry, beg pardon, n plus 1 times n factorial is just n plus 1 factorial.
Okay.
Is that? So that means that 2 times n factorial must be less than or equal to n plus 1 factorial. Then I went back to the thing that we had on the left side before we went across. I'll just fill it in.
And that give us that. So we end up with 2. We end up with the 2n factorial equal to n plus 1 factorial.
Say it again?
Where you have, because the thing that you wrote with the 5 times the 4 factorial equal to 5 factorial, that principle is what you use to get the 2n factorial to be equal to n plus 1 factorial.
Less than or equal to it. Equal to it.
Less than or equal to n plus 1 factorial.
Right.
Okay, continue from there.
So just fill that into the left, because you see that. Alright, I'm gonna underline some stuff right now, or circle them so you can see what I'm talking about. Right here, you see that 2 to the n less than or equal to 2n factorial?
Yes.
It's the same thing we have. So that 2n factorial, this part, if we go on the right side now, we have shown that 2n factorial is less than or equal to n plus 1 factorial. So just use that bit of information right here now on the left side. That's what I use over there.
All right. Last one. I didn't get that.
So on the right side, I showed that 2 times n factorial is less than or equal to n plus 1 factorial. That's what I showed on the right side.
Yes.
Then I brought it back to the left, to the line that we had above, that the underline in green. I just added that bit of information beside it to show that 2n factorial is less than or equal to n plus 1 factorial. I just included that.
Okay.
You get it?
So it's a matter of substitution.
You can call it that.
Where we have the 2n, 2 to the power of n. The 2 to the
less
power
than or
of
equal
n.
to 2n factorial.
Less than or equal to 2 factorial. And 2 to the n factorial is equivalent to the n plus 1 all factorial.
Equivalent to it, less than or equal to it.
Less than
That's what you want to write, you know. I think you're confusing the equal with the less than or equal. Look here. In the line above, maybe it's because I write it like that. All right, you have everything written in the book, right?
No, sir. Because, sir, I'm not going to write it, I don't understand.
No, man, write it, because I need to erase the book quickly. Write it quickly.
All right, I did that.
Michaela, Anthony, LaFern, everything okay with you guys with this? What am I so quiet? It's okay, Anthony's okay. Michaela, let's see, Michaela is here.
Okay, sir.
Yeah, she's here.
I wrote it off.
Oh, she's good, okay. You watch it off?
Yes, sir.
All right. You see that purple and orange? I'm going to show you what's happening over there because you keep saying equal. I want to make sure you see that it's not equal. Follow me now. I have 2. What kind of color is this?
Green.
I can barely see the 2 light. All right. If you have 2, what I did was this. 2 is less than n plus 1. We agreed on that. Sorry, less than or equal to n plus 1. We agreed on that because n can't be any less than 1. The number n, whatever it is, it has to start from 1 and go up because n must be a natural number. So that statement is true. So having accepted that statement, we now multiply both sides by n factorial. N factorial times the right, and sorry, times the left, and n factorial times the right. But n plus 1 factorial, rubbish, n plus 1 times n factorial is equal to this. I'm going to write it down here. N plus 1 factorial. This is equal to that. Good? Which means that 2n factorial must be less than or equal to n plus 1 factorial. I think you were confused because I wrote the equal below it. It looked like I was saying 2n factorial is equal to that. What I was saying is that this thing up here is equal to n plus 1 factorial. Not the 2n factorial. You get that now, Jermaine?
Yes, sir.
All right, so because 2n factorial is less than or equal to n plus 1 factorial, it means that what we had before in the blue writing, 2n factorial was less than, what did I have again? I think I did have 2, no, rubbish, I wrote the wrong thing, sorry. I wrote the wrong thing. It should have been 2 to the n was less than or equal to 2n factorial, which we just showed a while ago is less than or equal to n plus 1 factorial. So because the left is less than the middle and the middle is less than the right, it means that the left must be less than the right. That's what we're showing.
Okay, sir.
All right, so I think you were thinking that I had this, but this was never the case. At no point in time did I have 2n factorial is equal to n plus 1 factorial. If you were thinking that, that's where you probably get confused.
Okay,
It was
sir.
never equal to it, it was less than it. Less than or equal. All right?
Yes, sir.
Good. All right, so let me show you the other one. So this is the proof when n is just the number. What's going on here? Give me a minute, please. Play zone. Zone is here. Oh, this one. Sure. What is it? All right, back to what we're doing. So the next one I want to show you. Let me show. So I'm going to. That was principle number 1. Principle of induction number 1. I'm going to show you one now using principle of induction number 2, where you have 1, 2, 3, 4 right up to k. So let's prove this. So write this down. Show that for all c. Show that for all c. I don't like c no. You write c already? Should I say x? All right, stick with c. Show that for all c not equal to 1. So for all c not equal to 1, 1 plus c squared plus blah blah plus c to the n is equal to 1 minus c to the n plus 1. I'm going to squish everything like this. So show that for all c not equal to 1, 1 plus c squared plus c cubed plus blah 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 blah. C to the n is equal to 1 minus c to the n plus 1 over 1 minus c. The Access students should have seen this before. Well, should have. I don't know if they have, but they should. All right. Ready to prove it now?
Yes, sir.
All right. So guys, what's the first thing we would do? God have mercy. Nothing is remember this. We just did a while ago. The first thing we would do is what?
So show that C1 is true.
Show that C1 is true. Not C1. P of1.
F1, yes.
All right. So remember this, we are going to use this as our P of n. That statement, let's write the P of n right here. That is our statement. That 1 plus c squared plus c cubed plus blah, blah, blah is equal to 1 minus c to the n plus 1 over 1 minus c. That is our statement, P of n. So for P of 1, we are showing that P of 1 is this, right? On the left side, we're going to have 1 plus c to the 1. We don't know if it's equal yet, so put a little question mark over it, like what we did a while ago. We're going to check to see if it's this, 1 minus c to the 1 plus 1. Replace the ends with 1 over 1 minus c. On the left side, all we have is 1 plus c. On the right side, we have 1 minus c squared over 1 minus c. But you all learned in college algebra, or if you skip college algebra, you learn it somewhere else, the difference of two squares. 1 minus c times 1 plus c. So the 1 minus c's cancel. 1 cancel that one. So we're left with 1 plus c is equal to 1 plus c. So it is true for n equal 1. Any questions about that? If not, write quickly.
Hello? Hello? Sir, can you hear me?
You're really low, Anthony.
Can you hear me?
Sarah left the chat. I mean, not the chat. Sarah, it's like he got kicked out. Um, to answer your question, Anthony, remember that you're plugging in one because so it's P1. That is the least element, P of one rather. So it's the one would be C0 plus C1. You're not going further than C to the 1 because the power represents n. So C of n. So C to the 1 because you're trying to find what P of 1 is. So that is why he has 1 plus C to the 1. You would have C to the 2 or C3 or any other um anything else because you're not going further than the first element, which would be 1. It's from the question. You're trying to prove that the left-hand side is equal to the right-hand side. So, um, for the left-hand side, you have 1 plus c squared plus etc. etc. c to the n is equal to 1 minus c to the n plus 1 all over 1 minus c. So you're trying to prove that the left side is equal to the right side. We're comparing both sides. That is why we're comparing both sides.
Hello, sorry about that. There was a disconnection because of the power cut, and Wi-Fi takes a while to come back up. Just make sure, are you guys hearing me?
Yes, sir.
Okay, great. All right, so the left side, sorry, not left side. Where was I? Yeah, we have just shown that it's true for n equal 1. So now we're going to show that it's true for n plus 1. After we have
Sir, you
assumed,
haven't proven. Sir, you haven't
what?
proven that it's true.
Yeah, man, we showed that the left side 1 plus c was equal to the right side 1 plus c. Remember we put n equal 1 in there? The first thing we had done was to check p of 1. We put the n equal 1 into the 1 plus c goes up to n equal 1. Remember, no, it's 1 plus c, 1, c, 2,
No,
c,
no,
3.
sir, I understand that, sir. So you're saying that from once both sides are equal in this case, then it's classified as one? Because what I'm saying that
No,
1
no, no, no,
plus
no, no,
c
no.
is equal to 1.
Listen. Once you replace n with 1, equal, then it is true for n equal 1. So the first thing I did was to replace n with 1. Show that both sides are equal. That means it's true for n equal 1.
Oh, okay.
All right. So we did that a while ago. So now we're going to assume that it's true for any n. Sorry, for n. Not any n. Oh, we're using the second one, so we assume it's true for k. So p of k would be 1 plus c plus c squared plus dot plus c to the k. That's a k. If I can make it better, probably look worse. Is equal to 1 minus c to the k over 1 minus c. So we have assumed that is true. We're now going to show that it's true for p of k plus 1 or p of n plus 1. Same thing. So I'll just use n because n is at the right. So p of n plus 1 now. Remember, we have assumed that p of n is true, you know. Oh boy. P of n plus 1 would be the statement 1 plus c plus c squared plus, oh, I made the same mistake I made last time. I didn't show you what I want to get. Let's write in the next line. Plus dot plus c to the k plus 1. Okay, I'm messing up because it was n. Sorry. Let's go this quickly. We have assumed this to be true. Pn, pk, same thing. 1 plus c plus c squared plus dot 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 plus cn. We have assumed to be true to 1 minus c to the n. I will go wrote k, but it's easier for me to write n on this board. That's the good n. nk doesn't matter. So don't worry about letter. As long as you write assume true, make sure you put that at the front or the end. You're assuming that it's true. Now, let me show you what we want to get. For the p of n plus 1, we want to get this. We want to get to the stage where we can show that 1 plus c squared plus c squared plus dot 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 plus cn plus cn plus 1. We're going to increase it by 1. We want to show that is equal to 1 minus c to the n plus 1 over 1 minus c. That is our goal. So we can put it in a different bracket so we can, that's what we want to get to. All right. So what we're going to do now is check p of n plus 1. So p of n plus 1, remember you can just put the thing in there. We're now adding cn plus 1 to both sides. That's how you do these induction steps. You see, for the first principle, we just put the number in there and check both sides. But for this principle, what we have to do is show that if you add it to both sides, the cn plus 1 to both sides, the result stays the same. So on the left side, we have 1 plus, so remember you need to use what you assumed as well. 1 plus c squared plus dot 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 plus cn plus c to the n plus 1 is equal to, on the right side, we're going to have this 1 minus c to the n over 1 minus c with an additional c to the n plus 1. That additional thing is there on both sides. So we've added c to the n plus 1, the term cn plus 1 on both sides. On the left side, though, look at this. Let me just highlight this portion. If you look on the left side, we have this. We have, what am I writing? No, the right side, beg pardon. On the left side, we have shown that this thing in brackets here is actually equal to oh, I'm looking at the wrong side. Sorry about that. Let's continue writing here. 1 plus c squared plus dot 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 plus cn plus 1. All we have to do is a little algebra on the right side. I was thinking too hard. So on the right side, we're going to multiply, we're going to add that thing. Remember the LCM is 1 minus c. So in the numerator, we're going to have 1 minus c to the n plus 1 minus c times c to the n plus 1 all over 1 minus c. For the left side, nothing changed. Just put the tilde. On the right side, we have 1 minus c to the n plus 1 times c to the n plus 1 minus I made a mistake somewhere now. I feel like I make a mistake somewhere. I'm confusing myself. Let me finish this. C to the n plus 2 all over 1 minus c. It's because I don't have the first part of the question. I feel that there's a mistake somewhere. I'm not sure where it is. Did you guys make a mistake somewhere? I just feel that I made one. I'm not sure where. Oh, I knew there was a mistake. We want to show this. Sure. Cn plus 2. 2 is what we want. Because this was supposed to be Cn plus 1 at the start. I knew there was something wrong here. So you see me putting in all the plus ones. Those plus ones should have been there before. 1 plus 1. So look up at the top. That formula should have been, the thing that we assume to be true should have been 1 minus c to the n plus 1. If you look back at the first part of the question I gave you. So when we include c to the n plus 1, c to the n plus 1 plus 1 is c to the n plus 2. So we want to show this thing up here, c to the n plus 2. Also, this was missing a plus 1 as well, right below the tick. The plus 1 was supposed to be here. All right, so sorry about that. I knew there was a mistake, but I just couldn't figure out where it was. Anyway, so these two cancel. That's c to the n plus 1 right here, cancels the c to the n plus 1 right here, leaving us with the left side equal to, so let me see if I can squeeze it in, 1 plus c squared plus dot 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 plus c to the n plus 1 equal to 1 minus c to the n plus 2 over 1 minus c. So see, we have shown what we wanted to get. So it is true for all n in natural numbers. Whew, sorry about that. Hope they make a mistake, didn't confuse you guys. I left out the n plus 1. No, nobody even said it. So remember that I don't have the first part of the question because I erased the board. So you guys had it in your book. I didn't have it. Anyway, any questions? If I'm going to do any more induction, I'm going to use my whiteboard because when I clear this board, I don't know what I had before. I don't remember. And it probably confuses you too.
Sir, erase it as it. I'm writing it off, please.
Yeah, man, no problem. Yeah, all right, yeah. Best to go over it. I can't go over it now because we're out of time. But next class, maybe I'll do one more and probably do it on my whiteboard so there isn't any problems. You see, stuff like this should not be taught online, but COVID and everything. So. Or if it's taught online, they should give me a proper laptop so I could get a nice fat camera.